the fourth question of CodeForces round 923 division 3 is find the different ones. Okay. In this question, you're given an array A of n integers and q queries. Okay. And each query is of the format L comma R. Okay. Now, what is asked in the query is that our task is to find whether there exists, our task is to find two indices I and j such that both of them lie in the range L to R and A of I not equals to A of j. Okay. Basically, they'll give you two indices. So let's say this is the test case, right? Let's say this is the text case. This is the array given to us. Okay. Right. And they have given me 5 queries, right? In the first query, it's 1 comma 2, which means that we need to say whether in this range, from first element to second, whether in this range, are there two elements such that both of their values are different? Okay. And in this case, the answer is yes, right? So if you look at the second test case first query, right? Second test case first query is, yeah, it says 2 comma 2 and 1. Basically, it means that 2 and 1 are those indices where I and j have A of I and A of j have different values. Okay. So similar way, we need to answer all such queries, right? And the n value can be up till 2 into 10 power 5, starting from 2. And array values can be up to 10 power 6. And the number of queries can also be up to 2 into 10 power 5. Okay. They've also mentioned to us that sum of n over all test cases does not exceed 2 into 10 power 5. And similarly, sum of q across all test cases also does not exceed 2 into 10 power 5. Okay. So one important condition. And L and R will be from the range 1 to n. Okay. So it's one base indices. All right. So yeah, let us see how we can solve this question. So let's understand the logic behind solving this question. So in every query, they give you two parameters, L and R, right? Which means we need to find from AL plus 1, AL plus 2, dot, till AR. We need to find in this range whether there exist two elements, I and J, such that two indices I and J, such that A of I not equals to A of J, right? This is what we need to find, right? Now, if there are no indices, if there are no two elements A of I and A of J such that they are equal, which means that all the elements in the array are equal to each other, right? If this condition never satisfied at any point for a particular L and R, then we can conclude that all the elements in the array will be equal, right? Now, in case this satisfies, we can say that there will be at least one point from this range, one point in this range such that A of I not equals to A of I plus 1. Okay. Now, the claim I'm making here is there will be two elements, A of I and A of I plus 1, two adjacent elements from adjacent elements in the array such that they are not equal to each other. Because if all the pairs of adjacent elements are equal to each other, then it becomes the array where all the elements are equal to each other, right? But since this condition has to satisfy, even this has to satisfy, right? So now to solve our question, keeping track of this value will be enough for us. Okay. Now this might seem confusing a little bit, but let's still go further and understand with the help of a test case how keeping track of this will allow us to find our answer. Okay. So let's take a test case like 1, 1, 2, 1, 1, 1, 2, 1, 2, 1. Okay. Let's say this is the array given to us. Right. Now I'll take another array. I'll call it differences. Okay. Now this array will basically store the value of all the indices where uh, all the indices I such that a of I not equals to a of I plus 1. Okay. Now, according to the question, so okay, if these are the indices, let me just give one base indexes. Okay, 7, 8, 9, 10. Okay, right. So please make a separation. Right. So these above values are the indices and these are the array values. Okay. Now, if we want to see at how many places these conditions satisfy, that we can do in a simple for loop, right? Simply just run a loop from 1 till n minus 1, right? Until this point. You just run a loop and just keep comparing the element and the element ahead of it. Okay. Now, from that, we can find out that element at index 2, we get two elements different. At index 3, also we get two elements different, right? And again, at index 6, we get two elements different, and index 7 as well, right? And again, at index 8 as well, and index 9 as well. So even 8 and even 9, right? Now we know that at all these indices, we got elements such that a of I not equals to a of I. Okay. Now we have kept track of these values, right? Now observe that these values will always be sorted because if you're running a for loop linearly going forward and finding these indices, then you can just simply show them in the order as they are. Okay. Right. Now, once you have this list with you, once you have this difference list with you, you can answer the queries in log n complexity by applying a binary search on this. Okay. Now let's see how that is possible. Okay. Now, so let's say you're given an L and R. Let's say your L value is equals to 4 and your R value and R value equals to 9. Okay. So you've been given with 4 and 9 as L and R indices. Okay. Now what I'll do is I'll take 4 and I'll apply a binary search on this and find the smallest element that is bigger than 4. Okay. Now, smallest element that is bigger than 4 is 6, right? It's the smallest element that is bigger than 4. Okay. And once you have found this element, just check whether this element is less than 9, right? Now, this element is less than 9, right? Which means that this index occurs between 4 and 9, right? And since this index occurs between 4 and 9, we can be sure that from 6 to 7, there will be point where the value at 6 and 7 is not equal, right? Values at index 6 and 7 are not equal, right? So based on, with the help of a binary search, if you find the largest element smaller than the L value, then we get our answer. Then we get an index value and just simply compare that with R and we can find our answer. So if this value, let's call this index, okay? If this index is less than R, then that means IDX and IDX plus 1 will be the answer. Okay. Now they have mentioned in the question that for each query we need to print two indices I and j such that A of I not equals to A of j, right? So after doing binary search, whatever index we find, if that index is less than R, then IDX and IDX plus 1 will be the answer. But in case the index is more than R, more than or equal to R, in that case, the answer will be -1 and -1, okay? Which basically indicates that there are no elements A of I and A of J such that A of I not equals to A of J, okay? So that is how we do it. Now, why did I say even for equal to case, okay? Let's say instead of, let's just erase this for a second. Let's say instead of having L and R as 4 and 9, let's say we had L and R as 4 and 6. Okay. Now we have L and R as 4 and 6, right? Now if we do a binary search on 4 and find the largest element, find the smallest element larger than 4, then we get 6, right? Now here, so the value of IDX equals to 6, right? Now here, the IDX value is equal to R, right? Which means IDX and IDX plus 1, these both indices have different elements, right? Which is basically 6th and 7th index, right? So 6th and 7th index, these have different ones, right? But the 7th index, basically it is R plus 1. So it is an index extra. So that's the reason why we put if, uh, that's the reason we put if IDX less than R. Instead of it, if IDX less than equal to R. Okay. So only in this case, it will be IDX and IDX plus 1 will be the answer. In all the other cases, it will be negative 1 and negative 1. Okay. Also, if there are no elements in the array that are different, equal to each other, basically, if all the elements in the array are equal to 1 or equal to any random number, right? In that case, then no matter what the query is, any subarray AL to AR will never have elements AI not equal to AC, right? Because even in the original array, all the elements are equal, right? So in that case also it will be -1 and -1. Okay. So handle that case. In that case, you're just avoiding doing this entire binary search process. Okay. So the time complexity of this approach, let's see. Time complexity of this approach will be n into log n. Okay. Log n because we are doing a binary search. Binary search works in log n complexity and it's log n base 2 for clarity. And the space complexity here will be O of n. Okay. O of n to store the array. Okay. So yeah, that's how we solve this question.